Hello and welcome to a new video on cryptography for everybody. In today's video, we will create our own homophonic substitution cipher. We structured this video into 4 different parts. In the first part, you will learn what a homophonic substitution cipher is. Then we will make the homophonic substitution cipher more secure by introducing doubles, nulls, words, and additional other things. Then we will make it even more secure by introducing what a nomenclator is. And finally, of course, we will do this in CrypTool 2. We will create our own homophonic substitution cipher. What is a homophonic substitution cipher? We first need to know what is a simple substitution cipher. And a simple substitution cipher replaces single letters by single letters, digit groups, or in general symbols. Examples for these simple substitution ciphers are the Caesar cipher, we already had a video about this, the simple monoalphabetic substitution cipher, we also had a video on this channel, or the pig-pen cipher, and here we also had a video about this. And simple substitution ciphers can be broken easily even by hand. For instance, with frequency analysis, or with the help of CrypTool 2, where we can use the simple substitution analyzer. And here is an example encryption where I encrypted a text with a simple monoalphabetic substitution cipher or simple mask. And to make it easy, to produce many ciphertext symbols, we use digits here, as you can see here. For instance, our key is H equals to 1, E equals to 2, L equals to 3, O to 4, W to 5, R to 6, and D to 7. And we can think of all the other letters of the alphabet having also a 2-digit ciphertext symbol assigned to these. And when we encrypt the text Hello World, we just replace each letter by the corresponding ciphertext digit combination. So we have 1, 2, and then this is really important for a simple monoalphabetic substitution cipher. By the way, monoalphabetic means that we only have a single alphabet. Also, the homophonic ciphers that we will see have only a single ciphertext alphabet. In this case here now, with the simple substitution cipher, the L is encrypted by a 03. And the next L is also encrypted by a 03. Same applies to the L at the end for the L in world. So with a simple monoalphabetic substitution cipher, each letter is always replaced by the same ciphertext symbol. In our case, it's 03. To make ciphers more secure, cryptographers in the past invented the so-called homophonic substitution ciphers. And a homophonic substitution cipher has more choices, and we call these choices homophones for encrypting letters or pieces of text. An example encryption with a homophonic substitution cipher is like this here. So we have again Hello World that we want to encrypt. And for some of the letters we have homophones or different homophones. And for example, for the L we have the choice between 03 and 04. And for the O we also have a choice. We have 05 and 06. And we could think of all letters having choices. And the more choices, of course, you have, the more difficult it is to break such a cipher. And now in our case here, you can see that the L's are encrypted by different ciphertext symbols. We have the first L encrypted by 03 and the second L encrypted by 04. And then we have another L here at the end. This is the L of world. And we once encrypted it again with 03. So we have different choices, different homophones for the plaintext letters. But this is still a monoalphabetic substitution cipher. That means we have always the same ciphertext alphabet. So we have never the possibility that, for instance, 03 or 04 encrypts another plaintext letter than L. So 03 and 04 always encrypt L. With a polyalphabetic cipher, it could be that we exchange the assignments here, that we choose another ciphertext alphabet, and then the 03 and 04 could be assigned for other plaintext letters. But in our case, as homophonic substitution cipher is also, and this is always for homophonic substitution ciphers, these are monoalphabetic substitution ciphers also. Now let's have a look at two examples here. I have an example plaintext here in cryptography, a substitution cipher, and so on. So this is an English plaintext. And we encrypted it 2 times, first with a simple monoalphabetic substitution cipher, where we assigned the A to 01, B to 02, and so on. So Z, the last letter in our alphabet, is 26. And we encrypted the text using this key here. And we did the same with the text here, but also with a homophonic substitution cipher with a homophonicity of 3. Homophonicity of 3 means that we have for each of the alphabet letters 3 choices. So we have 3 ciphertext symbols for A, 3 ciphertext symbols for B, and so on. Each letter in our plaintext alphabet has 3 possible ciphertext letters. And of course, at a first glimpse at these 2 texts, you don't see anything here. So you don't see differences. Of course, you could have a look at details of this text, and then you will see that some of or many of these letters or the ciphertext symbols differ. But to ease this, we also created frequency analysis of these 2 texts. On the left side, you see the simple substitution cipher. You see the distribution of our 27 different plaintext letters. So we have 27 different ciphertext letters. Why do we have 27 and not 26? In our cases here, we also encrypted the space symbol. The space symbol in the simple substitution cipher here is encrypted using 00. And since the space symbol is the most frequent symbol in our text, or the most frequent, you could say, letter in our text, it has the highest frequency. And then we have the other letters here. And these letters then are also encrypted using a digit combination, a 2-digit combination. And you can see here the distribution of all letters. And for instance, this here is probably the E, and this here is probably the N. These are the most frequent letters in English. And we did the same with the homophonic substitution cipher, as I said, with a homophonicity of 3. So we have chosen 3 different ciphertext symbols for our homophonic substitution cipher. And here we have in total 70 different ciphertext symbols. This is because some of the plaintext letters only occur once or one time or twice. And therefore we didn't use all homophones for these letters. But as you can see here, this is a very big table, you could say, a very big graph with 70 different ciphertext symbols. But what we can also see with homophonicity of 3 here, with the equal distribution of our homophones, we have very different frequencies. And this eases it also to break the cipher, since very frequent letters like the E or the N here will also appear here very frequently. So possibly these 6 letters here are E and N in our encryption, I assume. And also, and I know that, this here is a space symbol. We have 00 for the space, and we added additional homophones for the space. So these 2 here will also possibly be space symbols. And the problem here is that we have equally distributed homophones, and we have 3 homophones for each letter. And to reduce these differences here, or to make it more difficult to break, it is smarter to assign homophones or more homophones to letters that are very frequently used in the language. For instance, to assign more homophones to E and N, and to assign very few homophones to very seldom letters like W, X, Y, and Z here. And we did this on the next slide. These are much or not as much homophones as with the homophonic substitution cipher on the previous slide. We only have 41 different ciphertext symbols here, so less homophones. But we assigned these homophones not equally. So we have not a homophonicity of 3. We gave to more frequent, or we used for more frequent letters in the plaintext, like E and N, more homophones. And we only used, for instance, 1 homophone for W, X, Y, and Z. And what you can see here is that these frequencies are closer together. That makes these harder to analyze, because in a perfect world, we would have all frequencies be at the same probability or at the same level. It would be a perfect, or not a perfect secure, but a very secure cipher to break, because it's very difficult then to distinguish these homophones. And you can see, for instance, I think this here is letter K. It only appeared a very few times in our text, and we only gave one homophone to this. But the other symbols, or the other ciphertext symbols, more or less are equally, or the frequencies of these are equal more or less. And so it's smarter to assign homophones or more homophones to frequent letters in the plaintext as to non-frequent letters in our plaintexts. Now let's make our homophonic substitution cipher more secure. And we do this as people did in history when they created homophonic substitution ciphers. They introduced doubles, nulls, words, and so on. And homophonic substitution ciphers were not only built based on single letters. So we do not only encrypt an A with an homophone, a B with an homophone, and so on. We can introduce higher order text elements to improve the security. For instance, to improve the security, additional cipher elements, as I said, were introduced. For instance, doubles or double letters. For instance, we could assign a special homophone for AA, for NN, for TT, LL, SS, and so on. Then, of course, we could assign homophones to other frequently used bigrams or higher order n-grams. For instance, TH in English is very frequently used, HE also, IN, and so on. So we could assign homophones to these bigrams. And then, for instance, in English, ING is used very often, Z is used very often. So we could assign homophones to these higher order n-grams. Then another thing that people did in history is the introduction of nulls. And nulls are cipher elements that encode nothing to A, further change frequencies. So we could introduce randomly, or we could at random positions introduce null elements in our ciphertext that are elements that, as I said, encode nothing, but they change the distribution of our frequencies. Then, of course, this should confuse attackers that want to break our ciphers. And then also nulls could mark special cipher elements, for example, nomenclator elements, which are the code words of our ciphertext. And this brings us then later to nomenclators and nomenclatures. Then we could also encrypt complete words, and then we have a nomenclator. For instance, we could introduce ciphertext symbols for the, for and, with, to, be, of, from, so frequently used words. And finally, we could also introduce code words in, as I said, the nomenclator. For instance, we could introduce code words for the king, the pope, or for city names like London or countries, or for names of emperors like Maximilian, and so on. So each of these words or combination of words, even here the king, would get their own code symbol, their own ciphertext symbol. And 3 additional advices when you create your own homophonic substitution cipher, and what they also did in history. For instance, encrypting or even showing unencrypted word separators, these are space symbols, helps the cryptanalyst to break a cipher. So when you create your own homophonic substitution cipher and to make it more difficult to analyze, or for being analyzed, or to break it, you should not show the spaces, and you should even not encrypt or introduce ciphertext elements for spaces. Then creating a code or cipher which shows separations of ciphertext symbols helps the cryptanalyst to break a code in cipher. This is, you don't encrypt these, but you still keep spaces in your ciphertext. In original ciphertext that we analyzed, we saw that you have a very nice ciphertext, and then between each word you have a separator. Here you keep the spaces, and this also helps the cryptanalyst to break the code or cipher. Encrypting the spaces is more difficult for an analyst, but you shouldn't do both. You shouldn't encrypt spaces, and you should not keep spaces. And finally, ordering in a code or cipher helps the cryptanalyst to break a code or a cipher. That means that, for instance, you assign 01 to A, 02 to B, 03 to C. And when the cryptanalyst finds out that there is ordering, that there is a rule how you created your homophonic substitution cipher, it's very easy for him to deduce missing or remaining ciphertext symbols and to revert your key. So you shouldn't have ordered elements in your homophonic substitution cipher. Now let's have a look at what is a nomenclator. And a nomenclator is a cipher with a nomenclature. So the nomenclature is a code word table, and the nomenclator contains the cipher and the nomenclature. Here's an example. You have a cipher, for instance, you encrypt A with 01, 02, 03. And as I said, you shouldn't do this, but to make it easier for me to create the slides, I did this here. So you shouldn't have ordered ciphertext symbols. But let's have a look at this here. You have 1, 2, 3 for A, 0, 3, 4, and 5 for B, and C, and so on. Then we introduce ciphertext symbols for double letters, like AA, LL, TT, and you could do this for bigrams and so on, like 11, 12, 13, 14, and so on. Then we introduced 10 nulls here. So these are ciphertext symbols that you can just put into your ciphertext. They have no meaning, but they should lower the frequencies of our ciphertext, and they should also confuse attackers. And then we have here the nomenclature, these two parts. We have, for instance, words in the nomenclature like the, and with. These are words encoded or encrypted with 3-digit ciphertext symbols like 840, 841, 842, and 3, and so on. So these are our nomenclature elements. And we have also in our nomenclature here code words, for instance, for the king, the pope, Germany, France, England, the Netherlands, and so on. And 1, 2, 3, we also encode, for instance, numbers here. And we could even encrypt or encode here complete sentences like we need help with 9,400, we attack at with 9,401, and so on and so forth. And this here then is a nomenclator. Now that we know what a homophonic substitution cipher is and what a nomenclator is, let's create our own homophonic substitution cipher in CrypTool 2, and maybe we also extend it to a nomenclator. So let's go to CrypTool 2. I'm here now in the Start Center of CrypTool 2. I use the newest nightly build, 92441. And in the Start Center, we could search, or we can search for our homophonic substitution cipher templates. And we have two templates. We have homophonic substitution cipher and nomenclature for encryption and for decryption. And I open the template for encryption. We don't need this here. And I think we need more space. And I think my head is in the way. So I will move this all. And I will also increase the size. Okay, this has to go here. This has to go here and here and here and here. Okay. The lines here are a little chaotic. So we have here our nomenclature or our key. I think key is better. And this key here, we have two, what are these CSV reader components? These split our key into different parts, and these parts then are given as plaintext and ciphertext alphabet to our substitution component here. Now I want to increase the text size a little. And here also, I think I will keep here our example text. And now, how can we create our cipher here? First of all, we have here our space. I will remove all of the assignments in the key first, and then we create a brand new key for the homophonic substitution cipher. Now I removed all the elements from the key here. And as you can see, we have here a space symbol. So how does this work? We have these brackets here. Then we have a semicolon, and then we have again brackets. And the substitution component understands the syntax here. So for instance, we have here a space between the brackets. Then we have the semicolon. And the semicolon says on the left side, we have our plain text symbol. And on the right side, we have one or more ciphertext symbols. These are then split into two different alphabets using the CSV readers here, the comma-separated reader components here. And the substitution component then uses these for encryption and decryption. And as I said, this here is a space symbol. And when I want to encrypt the space symbol, let's encrypt it just for fun to space. And when I now press play, we only see the space symbols here, since we have no assignments for our other letters. And I stop this now. And now we have to assign homophones to our mapping here. And as I said, I don't want to, or it's not a good idea to create ordered homophones. So I could start with 0, 1 for A, for B, for C, and then go on. And it's not a good idea to assign to each letter the same amount, or it's not needed to assign to each letter the same amount of homophones. For instance, X, Y, and Z, they only need very few homophones. And what I do when I create, for instance, okay, you won't create a homophonic substitution cipher as a secure cipher. This is only for fun and for letting other people try to break these. And the creation of these is also interesting for creating new algorithms to break these. And I created many of these ciphers, for instance, for lectures or for workshops, also for Mystery Twister, which is a cipher contest, and also for testing my own analysis algorithms. And when I usually create these, I try to create these as secure as possible or as not secure as possible, depending on what I want to analyze with or what I want to test with respect to my algorithms. So let's start, for instance, with the most frequent letter in English, with E, and we assign to E 05 and 09. Then we assign two homophones, for instance, to the N, 08 and 01. And we have to keep or to assign homophones only once. So I assigned to all the letters homophones. Maybe we assign a few more to the E, 29, 35. Maybe to the I also, 34, 39. And now we have some assignments. And I think I want to have at minimum 2 homophones for each letter. So it was, of course, not for V or for W, X, Y, and Z. And as you can see here, the pipe symbol separates our ciphertext symbol. So you have the choice, for instance, for A between 11 and 15. That's why I use the pipe here. I probably assigned a few ciphertext symbols twice. Usually when I create these ciphers, homophones are assigned twice. Okay, I don't like that the space here is encrypted as space, so we can change this to space. And what you can also see here is when we go to the substitution component, we have to stop this. We have here input and output separators, and we have a space as the output separator. When I remove this space here and then press play, we can see that we have no space at all as the separation. This could make it more, or this makes it more difficult when you want to attack such a cipher, because you don't know which of the digits belong together. When I have a separator between these, then in this case an attacker sees, or in this case not, but let's stop it and let's change it back to space, and we remove the space here, or let's encrypt the space with 00. Then an attacker can see, okay, all the ciphertext symbols consists of 2 digits. But when you remove the space here as the output separator, you only have this huge amount, or this bunch of digits. And an attacker cannot see that these are 2 digits. Now, when we put this here into the component, let's test if we still can decrypt it. Yeah. And not knowing the number of elements makes it very difficult for an attacker. And I just revert this and I just change this back to output separator and of course encryption. And now we have our cipher. So let's make it even more difficult to break. And this is why we introduce our frequently used bigrams and double letters. So let's introduce the TH as a bigram. And to make it a little more difficult, I now introduce 3 digits for these bigrams. Okay, after some debugging, I think I fixed the problem. I removed some of the homophones that were assigned twice. And now let's put back, or let's put into our key the. So, and we have to change this, of course, to encryption. And then we have here the. And to make it prefix free, we could use 601. So this 6. And now let's test if we now can decrypt it without any problems. And now it works. Yes. Okay, now we can go on and add more words to our cipher. So we have Z, then we could encrypt TH also, or not TH, let's encrypt END, 602. 2 we could encrypt, 603. Then off, 605 and 604. And then here are some words. And now I also want to encrypt some higher order words or code words like bishop. And here I use 7. Then we have Rome, I think, in our text. We have church. This is 2 and 3. And Jesus we have also in the text. And this is 704. And now let's press play. And let's test if we can still decrypt it. And I think this still works. We could also encrypt Peter with Peter in the text as a name. 708. And we have heaven. In this way, you can create a nomenclator with a nomenclature here. And of course, we have to change this to encrypt. And we have our ciphertext here, which only consists of digits. And then we can decrypt it. And this also works. And using the substitution component, we can create nice texts. And there's one final thing that I just added a few days ago that is, I think, quite nice. And this is handling of line breaks, because there was a viewer of this channel, and this is also why I make this video here, who asked if we could also encrypt line breaks. So we have here line break now in our text. Oh, and we also want to maybe encrypt for fun the dot here to, I don't know, 99. And we want to encrypt the line breaks. And the line break here can just be encrypted by using \n. This identifies the line break. When I now encrypt the text, of course I forgot to change here to encrypt. Then we get here our ciphertext. And when I change this to decrypt and put in the ciphertext here, it should also, yes, encrypt the full stop here, and it also encrypts the line breaks to 88 now. And using this, you could also create a formatted plain text, and then when you decipher or decrypt it using CrypTool 2 with the substitution component, of course, with the correct key, you get a nicely formatted text. Yeah, and now you could use the the substitution component also to create a homophonic substitution cipher using CrypTool 2. And there, this is everything I wanted to show you in this short video. I hope you liked it. If yes, please give a thumbs up. And also, if you did not yet subscribe to this channel, please do so. This really helps us to grow the channel and to make CrypTool 2 more popular. So, thank you very much for watching and see you in the next video.